All right, let's dive straight into our sources today. We've got quite a mix.
We certainly do, starting with some serious climate impact in India.
Yeah, first up, these really intense heat waves hitting Andhra Pradesh and Telangana. We saw reports, what, mid-May?
Mm,
Parts of AP over 41 degrees Celsius.
And before that, pretty much all of Telangana was hitting 40 plus. That's consistently dangerous heat.
So what's making it so bad in these specific regions? Is it just general warming or something else?
Well, it's a combination of things, geographical factors mostly. They're close to the Tropic of Cancer, so they just get more intense sunlight, more solar radiation. Mahesh Palawat from SkyMet mentioned that.
Okay.
And Telangana, it's landlocked, right? No big oceans or seas nearby to moderate the temperature, so you get that continental climate effect, hotter summers, colder winters.
Makes sense. And the land itself. I heard the Deccan Plateau plays a role.
Yeah, absolutely. Palawat pointed this out too. It's rocky terrain, lots of black soil, which, absorbs and holds on to heat much more effectively.
So the ground itself is like a radiator. How does that compare to, say, greener areas?
That's a key point. Vaimal Mishra from IIT Gandhinagar highlights this. Regions with a lot of agriculture, especially irrigated agriculture or dense forests, they benefit from evaporative cooling.
Ah, right. Like sweating, but for the land.
Exactly. Water evaporates from the soil, from plants that process uses energy, heat energy, and cools the air around it. It's a natural air conditioner, basically.
But in Andhra and Telangana?
There's less of that effect, especially in summer. Dr. Mishra notes there isn't much agriculture happening then, minimal irrigation. So, less moisture in the ground means less cooling.
And research actually backs this up. Irrigation helping cool things down.
Yes, Dr. Mishra mentions specific studies showing irrigation can suppress heat waves. Add to that, as Palawat said, less pre-monsoon rain means clearer skies, more direct sun. And deforestation doesn't help either. Fewer trees mean less evapotranspiration.
Wow, okay, so it's a perfect storm of factors. Are we getting better at predicting these specific events?
That's a challenge. Dr. Mishra points out a need for better early warning systems, maybe based on hourly data, which aren't fully there yet. He also thinks we need to differentiate mitigation strategies based on type of heat dry versus humid because they affect people differently.
Okay, really important points there. Let's shift gears now to something focused on solutions in agriculture. This World Food Prize winner, Mariangela Hungria from Brazil.
Yes, this is fascinating work. She won for her research on biological nitrogen fixation, basically challenging the massive use of chemical nitrogen fertilizers.
How does that work using bacteria?
Exactly, harnessing specific soil bacteria that can pull nitrogen gas from the air, which is abundant but unusable by plants directly, and convert it into a form plants can use. It's nature's way of fertilizing.
But farmers rely heavily on synthetic nitrogen. Was it tough to get them on board? Chemical fertilizers are, the standard?
It definitely was initially. Even though everyone knows the downsides of chemical fertilizers' greenhouse gases, water pollution changing habits is hard. Hungria spent decades identifying the best bacteria strains and understanding how they work with plant roots.
So lab work mostly.
A lot of lab work, but crucially, she took it to the field, worked directly with farmers, set up test plots to show them, look, you can reduce or even stop using synthetic nitrogen and still get great yields. Seeing those results on their own land made the difference.
And it worked particularly well for soybeans. Brazil is now the world leader, right?
Hugely successful with soybeans. The article mentions an interesting contrast with the U.S., where soybeans are often rotated with corn. The corn leaves behind some nitrogen, so the soybeans don't need as much added.
Ah, I see. So Hungria's method helped build up that nitrogen naturally in Brazilian soils.
Precisely. Using these bacteria helps enrich the soil over time. Of course, there's the whole issue of deforestation in Brazil for farmland.
Right, that's a common criticism.
Right. Hungaria's argument, though, is that by making existing farmland more productive and building healthier soil, her approach actually reduces the pressure to clear more land. Proper crop management, she says, feeds the soil.
It's a compelling argument. A truly transformative impact, it seems.
Yeah. Gabisa Ejeta, a previous laureate, called her work transformative for South America. The award ceremony is later this year.
Okay, let's move to another agricultural innovation. This time closer to home, India's genome-edited rice. ICAR developed 2 varieties, claiming it's a first.
Yes, a potentially major step. They're expecting seeds to be available to farmers quite soon, maybe within 6 months, and large-scale cultivation in the next few seasons. The varieties are DRR Done 100, or Kamala, and Pusa DST Rice 1.
And these aren't just minor tweaks. Kamala, derived from Samba Masuri, apparently has better yield, drought tolerance.
A
What else?
higher nitrogen use efficiency, which is great, and it matures about 20 days earlier. That earliness is significant.
How so?
Well, think about it. Less time in the field means potentially saving water, maybe needing less fertilizer, and possibly even cutting down methane emissions from the paddies. They've tested it widely, 225 locations.
And the other one, Pusa DST Rice 1.
That one's tailored for salty conditions. It shows much better yields compared to its parent variety, MTU 1010, under various types of salinity stress, inland, alkaline, coastal, really important for those challenging environments.
Now, the technique used, genome editing, specifically SDN1 and SDN2. Dr. Viswanathan from IRRI made a point of saying these are not GM crops.
Right, that's a key distinction they're making. Unlike traditional GMOs where you might insert a gene from a different species, that's SDN3, SDN1 and -2 involve making precise changes, like edits or deletions, within the plant's own DNA. It's more like accelerating natural mutation processes.
So proponents argue it should be regulated differently.
Exactly. Dr. Viswanathan notes that several countries are already exempting these types of edits from strict GMO regulations. They see it as closer to conventional breeding, just much faster and more precise. The research on these varieties is being published too.
But it hasn't been smooth sailing. There are objections.
Yes, some significant pushback. A former ICAR governing body member, Venugopal Badaravada, called the claims premature, demanding more transparency on the data. And the Coalition for a Genetically Modified Free India raised concerns about safety, precision, and the potential impact on farmers' rights and seed sovereignty, especially regarding intellectual property.
So the debate around genome editing in food is definitely alive and well here. Lots to unpack as these varieties roll out.
Absolutely. Transparency and farmer impact are critical issues to watch.
Okay, shifting focus dramatically now. Let's talk about the India-Pakistan situation. There's analysis suggesting a new era of warfare based on recent events.
Yeah, the source frames the recent standoff, Operation Sindoor, as potentially marking a real shift. It's not just about traditional military clashes anymore. Drone warfare is presented as perhaps the most revolutionary aspect.
Using lots of cheaper drones instead of expensive jets, that asymmetry idea.
Exactly. The source mentions PM Modi commenting on this, and it cites reports of India intercepting, 300 to 400 Turkish-made drones across dozens of locations. That indicates a scale we haven't seen before.
So drones like the Sky Striker Kamikaze aren't just for spying, but for probing, targeting, with less risk.
Right. Gathering intel, testing defenses, conducting precision strikes without putting pilots in harm's way. It changes the calculation of aerial warfare, and consequently, air defense has to evolve too.
How so?
It becomes about layered dynamic networks. The piece mentions India's system using indigenous tech like Akash and QRSAM alongside imported ones like S400 and Barak 8. LT Gen Rajiv Ghai is quoted on this, plus systems like Akashtir to help manage it all in real time.
Beyond the hardware, there's also talk about information warfare, disinformation campaigns.
A huge element. The analysis highlights Pakistan allegedly using digital platforms for psychological warfare, spreading doctored videos, false claims, trying to sow confusion and damage morale. It's a battlefield of perceptions.
We see that in other conflicts too, right? Like Russia-Ukraine. Controlling the story is vital.
Absolutely. And it reinforces the need for technological independence. India's push for indigenous platforms like Akash and Project Kusha is mentioned in that context. It's about not being reliant on others for critical defense tech.
The analysis also suggests a change in India's strategic thinking, more proactive.
Yes, a potential shift from a traditionally defensive posture towards something more proactive, focused on precision strikes and sophisticated escalation management signaling capability, without necessarily going to full-scale war. The PM's May 12th address is referenced as potentially hinting at this.
So what are the core elements of this shift?
The source outlines 3 things. Rapid response with measured force, that comprehensive layered defense and offense using both local and foreign tech, and advanced ways to control escalation. Better joint operations between the services, helped by things like the IACCS system, are also key.
But doesn't this tech also become available to adversaries, potentially making things more dangerous?
That's the flip side. Democratized technology enables asymmetric capabilities, which poses challenges. The conclusion is that modern conflict is multidimensional victory. Isn't just about land, it's about mastering technology, information, and psychology together.
A complex picture indeed. Okay, finally, let's turn to the world of material science, creating atomically thin 2D metals. This sounds like something out of science fiction.
Well, it's been a goal for a while, really inspired by graphene. Graphene is that single layer of carbon atoms, and it has all these amazing properties because it's so thin, basically two-dimensional. Scientists figured, hey, what if we could do that with metals?
What's the barrier? Why is it harder with metals than with carbon?
It boils down to bonding. Carbon atoms in graphene link up strongly side to side in a sheet, but the sheets themselves are held together by weaker forces, van der Waals forces. That's why you can literally peel graphene off graphite with sticky tape.
Okay.
Metal atoms, though, they really like to bond in all three dimensions. They form strong metallic bonds, up, down, sideways. So trying to isolate just a single layer is inherently difficult. They want to clump together in 3D.
People have tried before, right?
Yeah.
But not much success.
Yeah, for about a decade. Various techniques, depositing thin films, sandwiching them, even hammering them flat. But they usually ended up with stuff that was still many atoms thick, or had uneven surfaces, or oxidized really quickly. Not true. Stable 2D metals.
So what's the new breakthrough?
A study in Nature reports a new method. They call it a high-pressure sandwich technique.
Intriguing name. How does it work?
Okay, so basically they take metal powder, put it on a sapphire plate coated with molybdenum disulfide, MS2, that's the bottom of the sandwich. They heat it so the metal melts and spreads. Then they put another MOS2 coated sapphire plate on top.
The top slice of the sandwich.
Right. Then they twist that top plate just slightly, apply a lot of pressure, like 200 million pascals, and hold it while it cools. Then, carefully, they peel the layers apart, and hopefully a 2D metal sheet sticks to one of the MOS2 surfaces.
And it worked. How thin did they get?
It seemed to work for several metals: bismuth, gallium, indium, tin, lead. For bismuth, they reported a thickness of about 6.3 angstroms. That's roughly just 2 atoms thick, truly 2D.
Wow. What's the magic ingredient? The MOS2 and sapphire.
Seems to be crucial. They have very smooth surfaces and high stiffness, which apparently prevents the metal atoms from wanting to bond vertically. The pressure just forces them to spread out flat between these smooth, rigid layers. The bismuth they made showed electronic properties like a strong field effect that you only see in 2D materials, not in bulk 3D bismuth.
Has anyone else tried something similar?
A commentary by Javier Sanchez Yamagishi notes that growing thin crystals between these types of layered materials isn't entirely new, but he suggests using these large centimeter-scale MOS2 sapphire anvils might be the key improvement here, making it potentially more practical than other, more complex methods like molecular beam epitaxy.
So what could we do with these 2D metals? What are the potential uses?
Oh, the possibilities are pretty exciting. Because their electronic properties are expected to be so different, they could be used for things like hypersensitive sensors, maybe for medical diagnostics or military uses. Some 2D metals, like bismuth and tin, might even be topological insulators.
Which could lead to?
Potentially much faster, more efficient computers. Topological insulators conduct electricity only along their edges, which could reduce energy loss. There's also just the basic science learning about the fundamental properties of metals when confined to 2 dimensions, maybe combining different 2D metals, integrating them with other 2D materials. It really opens up a new frontier in material science and electronics.
Really fascinating stuff across the board today. Thank you for listening. If you want to provide suggestions or comments, contact on Twitter handle given in episode description.